So in this lecture, I will provide 3 applications of inequalities we proved so far. So the first application is a weak law of large numbers. So assuming that we have a family xj of independent random variables which are identically distributed. This means that these random variables are independent and that they have the same distribution. And I'm always here assuming that all these random variables are defined on the same space omega f and p. So these are independent random variables, and I will assume furthermore that these variables have a finite second moment, which means that x1 square is finite. Notice that since they have all the same distribution, this is also the expectation of xj square. And by Schwarz inequality, this means that they have also a finite first moment, so that the expectation of the absolute value of x1 is finite, and I will represent this expectation by m. So this is well defined because the second moment is finite. And what I might claim, so what I want to prove, is that, well, if I take the average of the first n random variables, so I take the sum of x1 with x2 and xn, divide that by n, I claim that this is close to the expectation of x1, which is represented here by m. And in which sense this is close? Well, in the sense that if I take the square of this difference and I take the expectation of this square, well, what I claim is that this is going to 0 as n is going to plus infinity. So I just wrote what we want to prove. We have a family of independent and identically distributed random variables. This is the shorthand for that, IID, independent, identically distributed. That will be used many times later on. I'm assuming that these random variables have a finite second moment. I'm representing by m its expectation to the first moment, and what I claim is that the expectation of this square is converging to 0. So let me give you a proof. Well, I will just, to shorthand, call y1 x1 minus m, and more generally yj will be xj minus m. So I can represent this expression as the expectation of y1 plus yn divided by n square. And what I claim, I leave it to you to check, is that this sequence of random variables, y1, y2, yn, so on, it's also an IID. But it's identically distributed. It's almost obvious that they are independent. Well, it's also clear, but I leave it to you to check. So these variables are IID. So let me expand this square. You have diagonal terms and off-diagonal terms. So the diagonal terms will provide me n squared times, well, the sum from 1 to n of the expectation of yj squared. And then the off-diagonal terms will give me 1 over n squared, the sum for j different from k of the expectation of yj, yk. Now this is equal, so I just expanded the square and I computed, I used the linearity of the expectation. So now let's recall that yj are identically distributed, so the expectation of yj squared is the expectation of y1 squared. So the first term is just the expectation of y1 squared divided by, well, they have n terms, and it's divided by n squared, so this is divided by n. And then for the second term, well, these random variables are independent, and we have seen that when they are independent, the expectation of the product, it's equal to the product of the expectation. So this expectation, it's equal to the expectation of yj times the expectation of yk. But the expectation of yj is equal to xj minus m. So the expectation by linearity is the expectation of xj minus m. The expectation of xj is equal to the expectation of x1 because they are identically distributed, and this is m. So all these two terms are equal to 0, and therefore these expressions vanish, and therefore we just proved that the expectation of this square it's equal to 1 over n times the expectation of y1 square. But this is finite because, well, y1 it's x1 minus m, so we can bound the expectation of y1 square by, say, the expectation of x1 square times 2 plus 2 times m. So this is finite, and therefore this expression converges to 0, and it converges to 0 at a rate of 1 over n, at least. So this completes the proof of my claim. So this is the claim we just proved. So now let me introduce some terminology. I will say that if I have a sequence of random variables, Zn, so this is a sequence of random variables, and let's say that we have a random variable z, I will say that Zn converge to z in L2, and I'm assuming this definition that all variables are defined on the same probability space. So I would say that Zn converge in L2 to z if the expectation of Zn minus z square converge to 0. So we just proved that the average of xj converge in L2 to the deterministic number m, which is the expectation of x1. This is what we just proved. Now let me make an observation, a very easy observation. Let's fix some number alpha, which is positive, and let's assume that we proved that xn is converging to 0 in the following sense, that the expectation of the absolute value of xn to the power alpha is going to 0. Right? So here again, I'm assuming that there is a family of random variables defined on the same probability space, and that we are able to prove that the expectation of the absolute value of xn to the power alpha goes to 0 as n goes to infinity. And this is what we proved here for the variables yj, for the average of the variables yj for alpha equal to 2. Right? So let me represent by xn bar the average of xj, and we proved that xn bar minus m, that this is converging to 0 in that sense with alpha equal to 2. Which means that we are proving that xn bar minus m is converging to 0 in L2. So what I claim, that then the following holds, that for all epsilon positive, so I'm assuming this condition, okay, and I'm claiming something else. So I'm claiming that for all epsilon positive, the limit as n goes to infinity of the probability that xn it's larger than epsilon, that this is equal to 0. So I claim that if this limit holds, then for all epsilon, this limit holds. And the proof is elementary and relies on Chebychev inequality. So since the function which associated to a positive real number x to the power alpha, it's increasing, it follows that if this probability, if xn is larger than epsilon, then xn to the power alpha, it's larger than epsilon. So this means that probability that xn larger than epsilon, it's less or equal than the probability that xn to the power alpha, it's larger than epsilon to the power alpha. So I fixed an epsilon, and well, since this function is increasing, this set, it's included in this set, and therefore the probability of this set, it's less or equal than the probability of this set. Now, I can use, at this point, Chebychev inequality to say that this is bounded by 1 over epsilon alpha times the expectation of xn to the power alpha. And therefore, it follows from our assumption that this quantity is converging to 0, which implies that this quantity is converging to 0. So let me say again, we just proved that if this limit, if this claim holds for some alpha positive, then for any epsilon positive, this probability is converging to 0. Well, let me apply this result to what we just proved, the weak law of large numbers. It follows that this expectation is converging to 0. So this assumption is satisfied for alpha equal to 2 and for xn equal to xn bar minus m. I'm sorry, there is some confusion here on the notation, but I think it's easy to understand what I want to say. Then it follows from this result and the observation, the comment I just stated, that for all epsilon positive, the probability that x1 plus xn divided by n minus m it's larger than epsilon, well, that as n converges to plus infinity, this quantity converges to 0, so the limit of this quantity. So let me summarize what we did up to now in this lecture. So this was my first example. We are considering a family of IID random variable with finite second moment. And we proved that the average of these random variables converge to m in L2. So this is the first claim, which relies on a simple computation. Then we observe the following. Well, if it is true that for a sequence of random variable, and let me change here the notation to avoid confusion. If we have a sequence of random variable Zn such that Zn, the absolute value of Zn to the power alpha converge to 0 in expectation, then for any epsilon positive, the probability that the absolute value of Zn is larger than n converge to 0. In particular, by applying this result to our previous weak law of large number, we get that for any epsilon, the probability that the average is far from m by epsilon goes to 0, whatever epsilon positive. Now, in this second application, I will fix a space omega and a sigma algebra F, and instead of having one probability measure defined on omega, I will have a family indexed by alpha. So alpha will be a real number between 0 and 1, and for each alpha, I have a different probability measure, which I'm representing by p alpha, which is defined on the elements of F. And I have random variables x1, x2, and so on in these. And these random variables are independent with respect to p alpha. So if I fix for all alpha these random variables which are defined in this space are independent with respect to p alpha. And they are identically distributed. But the distribution depends on alpha. So the probability under p alpha that x1 is equal to 0, it's equal to alpha, and the probability under alpha that x1 is equal to 1, it's equal to 1 minus alpha. So under this measure p alpha, these variables x1, say, take only two values, 0 and 1, takes the value 0 with probability, with probability 1 minus alpha, and it takes the value 1 with probability alpha, where alpha it's a fixed parameter between 0 and 1. Now, observe that, well, since these variables are independent, I leave it to you to check that if I consider the sum from 1 to n of these variables xj under the measure p alpha, well, these variables, this sum may take the value going from 0 if all xj are equal to 0 up to n if all xj are equal to n. So what I claim is that, well, this probability that the sum is equal to k, where k is an integer value between 0 and n, under the measure p alpha, this probability is equal to n choose k times alpha to the power k, 1 minus alpha to the power n minus k. So these are under p alpha, these random variables are called the Bernoulli, and this is represented by Bernoulli with parameter alpha. So these are IID Bernoulli random variables with parameter alpha. And this is, well, the sum of n Bernoulli random variables. So it has also what's called and denoted by p n alpha. So this is the sum of the distribution of the sum of n IID random variables which are distributed according to p alpha, where alpha is this parameter between 0 and 1. So these are just notation names for these variables, but so what I want you to check is that this identity holds, because we will need that for the second application, which I will present now. So I summarize here what we just introduced. We have a probability space, a measure space omega f, and on this measure space we have a family of measures p alpha, where alpha is a parameter, real number between 0 and 1, and under p alpha these random variables are IID with this distribution, and we computed the probability that the sum is equal to k. Now here's my application. Let's fix a function which is continuous and defined on 0, 1. And let me introduce for a fixed integer n what's called the Bernstein polynomials, which are defined as follows. Fn of x, it's equal to the sum from 0 to n, nj, x to the power j, 1 minus x to the power n minus j, times f computed at j over n. So f, it's a continuous function, and now for each n, I define this polynomial of order n, which is represented by fnx, And my claim, what I want to prove, is that, well, this sequence of polynomials converge uniformly to the function f. So the supremum for x between 0 and 1 of f and x minus fx, the limit of this expression as n tends to plus infinity, that this is equal to 0. So this is my claim, which I will prove now. And well, the idea is to use these random variables f in order to have a representation of these Bernstein polynomials. So let me compute f of the sum 1 over of the average of xj. So xj are these random variables. I take the average of these random variables and I compute f at this average. And let me compute the expectation of this expression with respect to the measure p alpha. So expectation alpha will represent the expectation with respect to the measure p alpha. Well, how do you compute the expectation? Well, these random variables take certain value. This sum will be equal to k with a certain probability. So I'll just sum over all the possibilities, and this sum takes the value k from 0 to n. We have seen that. The probability that this sum is equal to k is given by this expression. And if this sum is equal to k, this expression is equal to f computed at k over n. So the expectation under the measure p alpha of this expression is given by this sum. And you see that this is exactly the Bernstein polynomial computed at x equal to alpha. So this is fn computed at alpha. So now, if I want to express this difference, I can express this difference by using this expectation. So it follows from this identity that you fix an x between 0 and 1, and you write the difference fn x minus f of x by using this representation of the Bernstein polynomial in terms of this expectation. So this is equal to the expectation. Now you see alpha, it's x, so the expectation with respect to the measure px. And let me represent this average by xn bar of f computed at xn bar minus f computed at x. So here, I use this identity and then the linearity of the expectation to place fx inside the expectation. At this point, let me erase this identity, which to have some space. So we arrived at this point. Now, what I want to use is the fact that f is continuous and therefore uniformly continuous in the interval 0, 1. And so, remember that we want to prove this expression. I will erase it to continue my argument. Now, since f is uniformly continuous, for any epsilon fixed, I can find a positive delta such that if x minus y are less than delta, x and y are points in 0, 1, then fx minus fy, it's bounded by epsilon. And therefore, I will first use that the absolute value of the expectation is less or equal than the expectation of the absolute value. And then this is a simple property of the integral, which you have seen in measure theory. And then decompose this expectation in two pieces. One piece in which x n bar and x are at distance delta, and one in which they are at a larger distance. So let me first go step by step. So I claim that this is bounded. So I'm first introducing the absolute value inside. So I said it, but I didn't write it, that x n bar, it's the average of xj. Now I want to decompose this expectation in two pieces, which will be estimated separately. So the first one, it's x n bar minus f of x. And here I'm assuming that x n bar minus x, it's less or equal than delta. So I fix an epsilon. I obtain the delta by the uniform continuity of f. And this is the delta I'm using here. And then there is a second piece in which x n bar minus x, it's larger than delta, and this is the indicator function. So this is equal to 1 if x n bar minus x, it's larger than delta, and it's 0 otherwise. So you see that the sum of these two indicator functions is equal to 1, and we are using the linearity of the expectation. So now, when x n bar minus x is less or equal than delta, by the uniform continuity of f, by this expression, we have that this difference is bounded by epsilon. So this difference in this set, it's bounded by epsilon. So this is bounded by epsilon. This is bounded by 1. So the entire expression is bounded by epsilon. And therefore, the expectation, since the total expectation, total probability, it's 1, the first term, it's bounded by epsilon. Then we have to estimate the second term. But mind, the second term, the idea is to use the weak law of large numbers. Because we know that if you fix alpha, then, well, the variable x1, they are IID. They have finite second moment. So the weak law of large number can be applied to this sequence. And therefore, we know that xn bar minus x converge in L2 to 0 under the measure px. So this is what we want to use here to say that the probability of this event is very small. So since f is continuous, it's bounded. Therefore, this expression, it's less or equal than 2 times the L infinity norm of f times the expectation of this indicator function, which is the probability that xn bar minus x, it's larger than delta under the measure x. But mind that here, well, we want estimates which are uniform over x, because we want to estimate the supremum in x of this expression. So I can't just claim that this expression converges to 0. I have to show that it converges uniformly in x to 0. So if I wanted to prove just that fnx is converging to fx, I could just apply the previous result, saying that this expression converges to 0 as n goes to infinity. But we want a bound which is uniform in x, so we have to be careful here. And let me bound this expression by using Chebychev inequality. So we still have that this is bounded by epsilon times 2 times f infinity. Now let me take the square on both sides. So if this is larger than delta, then this expression, it's larger than, the square of this expression is larger than delta square. And let me use Chebychev inequality at this point to say that this is bounded by 1 over delta square, the expectation of xn bar minus x square. And now, well, let's compute again this expectation. And so if you repeat the computation we did in the first part of this lecture, what you get is that this is bounded by 1 over n times the expectation under x of x1 minus x square. So this is bounded by the same expression, epsilon minus 2 times f infinity divided by, and this expectation is bounded by this expression. So this is just, you can repeat the computation or recall the computation we did in the first part of the lecture. Now, what is the expectation of this expression? Well, x1 takes the value either 1 or 0. So it takes the value 1. And if it takes the value 1, this expression is equal to 1 minus x square. And it takes the value 1 with probability x. Then it takes the value 0. And if it takes the value 0, this is x squared. And it takes the value 0 with probability 1 minus x. So this expectation, it's equal to this expression, and this expression, it's equal to x1 minus x. And this is bounded by 1/4. So x takes value between 0 and 1. So the supremum of this function from x between 0 and 1, it's 1/4. And this is the value at x equal to 1/2. So what we proved is that the probability that we wanted to, the expectation, that we wanted to estimate, which was bounded by this expression, it's bounded by epsilon. We get 1/4, so here we get f infinity 2 times delta square, and this divided by n. So in conclusion, this computation yields that the supremum for x between 0 and 1 of f and x minus fx, that this is bounded by epsilon plus what I just wrote, which is f infinity divided by 2 delta square n. And therefore, if I take the limit as n goes to infinity of this supremum, of f and x minus fx, then this is bounded by epsilon. And since epsilon is arbitrary, sending epsilon to 0, we conclude the proof that fn is converging to f uniformly in the interval 0, 1. And this is the second application. So the third application, now it's an upper bound for large deviation. So again, we have a measure space, omega f, and we have a measure p defined on this space. And we also have a family, x1, x2, of IID random variables. And what I will be assuming now is that for all theta in R, this assumption is not needed, but I don't want to go to the most general case. I'm assuming that for all theta, the expectation of theta x1, that this is finite. so that you have these variables x have exponential moments, so that these expectations are finite. So let me represent by m the expectation of x1, which is well defined. X1 are integrable because, well, the exponentials are integrable. So this is well defined. And since they are, and also the second moment, it's also finite by the same reason. And so the weak law of large number and the observation tells us that for any epsilon positive, the probability that x1 plus xn divided by n minus m, that this is larger than epsilon, well, this converges to 0. This is what we proved so far. Now, what I want to take a number, a fixed number, and I want to investigate what is the probability that x1 plus xn minus m, it's larger than a. So I know by the first result that this probability goes to 0. Well, what I claim is that it goes to 0 exponentially fast, and I want to get an estimate on the rate of convergence of this expression to 0. So actually, so if this expression is larger than a, it means that either the probability without the absolute value is larger than a, or this expression is smaller than minus a, where a is this fixed number. So I will consider just one of the two expressions because they are estimated exactly in the same way. So I'll be interested in the probability that x1 xn divided by n minus n, it's larger than a. And in order to estimate this probability, well, let me take m to the other side, and let me take n to the other side, and take the exponential of this expression. So this is equal, or it's bounded by the probability that the exponential theta x1 plus xn, it's larger, let's say larger or equal, don't mind, that exponential n a plus n. And now let's apply Chebychev inequality to say that this is bounded by exponential minus a plus m times n expectation of the exponential of theta x1 plus xn. So notice that this inequality holds for all, I'm sorry, I forgot here theta. So let me go back. I first took m to the other side and multiply everything by n, and then multiplied further by theta, took the exponential. Theta here, it's a positive real number. I took the exponential and applied Chebychev inequality to get that this probability is bounded by this expression. Now, this expectation, it's equal to the product of the expectations these random variables are all independent, so the exponential of theta xj are a new family of independent random variables, which means that the expectation of the product it's equal to the product of the expectation. But these variables are all identically distributed, so this expectation does not depend on j. So what we get here is that this is equal to the expectation of exponential x1 multiplied by theta, and this to the power n. So if I define by m theta, so let me introduce a notation here. M theta will be the log of the expectation of the exponential theta x1. And I just want to do this in order to rewrite this expression. So if I take the exponential of m theta, I get that the expectation of exponential theta x1, it's exponential theta. So this tells me that this is equal to exponential n times m theta, right? Where m theta is given by this expression. So we just proved that this probability, it's bounded, let me write it here, by this expression, and I will put, so you see that there is n here and there, so I'll put this n first, and then we have minus a plus m times theta minus, or plus, I'm sorry, m theta. So now I will erase everything, and in the next take, I will start from this inequality which I just proved. So I proved that the probability that this average it's larger than m plus a, it's given, it's bounded by this exponential. So I summarized what we proved so far. We have a sequence of random variables which is IID. I assumed that these variables have exponential moment. I represented by m the expectation of x1, and by m theta, for theta positive, say, the log of the expectation of exponential theta x1. And what we proved is that for any a positive, then the probability that the average minus m, it's larger or equal than a, that this is bounded by this quantity. So this was what we proved in the last take. Now, what I claim is that m theta, it's a convex function. And this is what I'm going to prove now. So here's the definition of m theta, and I want to prove that it's a convex function. The fact that I assumed that all exponential moments exist mean that I'm able to take the derivative with respect to theta in this expression. So I will just take the derivatives, and I will prove that the second derivative of m theta, it's non-negative. So let's take the first derivative of m theta. We have a log, so we get 1 over expectation of exponential theta x1. And now we have to take the derivative with respect to theta of this expression. So this is expectation of x1 exponential theta x1. And by looking at this expression, what I want to write is that this is actually the expectation with respect to a new measure, which I'm representing by p theta, and therefore by e theta, the expectation with respect to this new measure of x1. And how do I define this measure p theta? Well, the expectation with respect to theta, this measure of a function f of x1 is, well, assume that f, so x1 takes value in R. So here f, it's a bounded, say, continuous function in R, and I'm defining this expectation. So this expectation, it's well defined because f, it's bounded, and it's given by the following expression. Well, fx1, expectation theta x1 divided by the expectation theta x1. So mind that we have in this way defined a probability, because, well, if f is positive, then this expression is positive. This expression is well defined because f it's bounded, and I'm assuming that x has finite exponential moments, so this is well defined. And it's a probability because if I take f equal to 1, then this is equal to 1. So this defines a new measure, say on R, because in this way I define what is the integral of any bounded continuous function, and this characterizes the measure on R. And with this notation, what appeared here is exactly the expectation of x1 with respect to this new measure. So now let's consider the second derivative of theta. Well, I will first take the derivative on the numerator, and this will give me the expectation of x1 squared expectation theta x1 divided by the expectation of exponential theta x1, and then the derivative of the denominator. So here I get minus this expression, the derivative of this one, but the derivative of this one, it's exactly equal to that one. It will give me x1. So actually what I have here, it's expectation of x1 exponential theta x1 square divided by the expectation of the exponential theta x1 square. And therefore, in terms of this measure E theta, which I just defined, what appeared in the first term, it's the expectation of x1 squared with respect to theta, to this measure theta. And in the second term appeared the square of the expectation of x1 with respect to this measure theta. Right? And, well, and this expression, it's larger or equal to 0 by Schwarz inequality. Right? So, indeed, the second derivative of m, it's non-negative, and therefore, actually, it's strictly positive unless x1 is concentrated on one point. But, okay, so assume that x1 is not concentrated on one point, and therefore, this second derivative will be strictly positive. So m will be strictly convex, otherwise it will be just equal to 0 because this expression will vanish. So this proves that, in any case, that m, it's a convex function as I claimed, and it introduced this measure, E theta, quite naturally. And we'll see later when studying large deviations that this measure plays an important role when we want to estimate sharply this type of probability. So we have this bound, and we prove that m theta, it's a convex function. Let me rewrite this bound as exponential minus n times a theta minus m theta. So I just want to bring m theta minus m theta to have a new function. So I just multiplied by minus 1, so I have a theta, which appears here, and then I have minus m theta and m theta. So let me consider this expression. So this is a convex, this is linear, so this function m corrected theta, which is m theta minus m times theta, it's still a convex function. let's compute its value at 0. And, well, here I will need the expression for m theta, which is the log of exponential theta x1. So if you take theta equal to 0, this is 1. So expectation is 1. I take the log, it's 0. So I get 0 minus theta equal to 0, it's 0. Let's compute the derivative at 0. So remember, m prime theta was equal to the expectation of x1 exponential theta x1 divided by the expectation of exponential theta x1. So now if I take theta equal to 0, this is 1, this is 1, so I get that this is m. So m prime at 0, it's equal to m. And therefore, what I get here is m prime at 0, which is m. The derivative in theta of this expression, it's also m. So what I have is that I just computed that m tilde is 0 at 0, its derivative it's also 0, and well, it's a convex function because m is a convex function, so the graph of this function in theta, it's a function which starts at 0, its first derivative is equal to 0, and well, it's strictly convex unless x takes only one value, so let's eliminate this case, and we get a strictly convex function, so m tilde, the graph of m tilde will look like that. It is 0 at 0, its derivative is 0 also at 0, and it's a strictly convex function. Now, what appeared here is that we can rewrite the estimate we obtained. It's exponential a theta minus m tilde theta. And you see that, well, the left-hand side does not depend on theta, so we can optimize this estimate in theta to say that actually this is less or equal than the infimum over all theta positives. We can place the infimum inside the exponential, and then when we have a minus, it gets a supremum, it becomes a supremum. So what we get is that actually this probability is bounded by minus n times the supremum for theta positive of a theta minus m tilde theta. And this is a function which depends on a, so let me call IA. So IA, by definition, is the supremum for all theta positive of a theta minus m tilde theta. And what appears here is that A, it's called the Legendre transform. So that's the name of a French mathematician. This is the Legendre transform of m tilde theta. Two observations. This is m tilde. Now what we are doing is we're taking minus m tilde, so we're getting a function which looks like that. It's 0, its derivative is 0, and it's now strictly concave. And on the one hand, on the other hand, we're adding a theta, a linear function. So this function, when you add, so the graph of this function will be something, it's now still 0 at 0, but its derivative, it's now positive, it's equal to a, and it's still strictly concave. So it's a function, you can show that it converges to minus infinity at infinity, and therefore, since it's strictly concave, it will assume its supremum at only one point, the point which satisfies the fact that A it's equal to M. So this is the point theta A. It's the point at which this supremum is attained. It satisfies this equation. Since M is convex, this means that the second derivative is positive. This means that the first derivative is strictly increasing, and therefore there is only one solution to this equation, and you can express theta A as this function is invertible, the inverse of A. And therefore you get an expression, explicit expression, replacing theta by theta A in this formula for the function I of A. But I don't want to do that. I just want to mention that the bound we obtained for this probability, it's given by exponential. So it decreases exponentially fast. So this is bounded by exponential minus n times a constant. This constant depends on A, and it's actually given by the Legendre transform of M tilde, where M tilde is given by this convex function. So this is the bound I wanted to present to you, which used only the fact that these variables are independent and have finite exponential moments. Just want to conclude this lecture with one remark. So here we have a convex function. For this convex function, we define its convex conjugated, or its Legendre transform, by this variational expression. And now, of course, since this is a supremum, it's true that A theta minus M tilde theta, that this is bounded by I of A. And this holds for all theta and for all A. And from that, we conclude that A times theta, it's less or equal than M tilde theta plus I of A for all theta and A positive. And this is a very useful bound. So you can think that A it's a function, theta it's a function, so you have fx gx, and you want to bound this product. You can bound this product by two conjugate convex functions. So this will be bounded by M tilde of fx plus I of gx, provided f and g are non-negative. So in conclusion, we obtained that this probability is exponentially small. We obtained a bound, and actually this bound you'll see later, it's sharp for this estimate, for the coefficient in front of the term n. And we obtained an explicit formula for I, which is the convex conjugate of the function M tilde given by this formula. So, and with that, I conclude this lecture.